Okay, there we go. So the possibilities of implementing the real stack, which is capable of storing not one single value, but series of values, and being able to also restore them, is going to take a little bit more, slightly more effort than just saying integer m value. So here's the plan. You may come up with your own ideas how to do this, but part of our homework perhaps is to play a little bit with arrays. We haven't done much work with arrays just yet, so maybe this is a good time to try something like that. So let's see. First of all, I'm just going to say debug, stop debugging. This is a very typical decision of mine. When I lose interest in this session, I instantly say stop debugging. Okay, so we stop the debugging and go back to our source. And we need to make some decisions on how to do things inside our stack. So it's scalable in terms of it can accept multiple push calls and save the value. So obviously it needs a more significant container other than single integer, right? Some sort of a collection of something, which in our case could be an array. So let me cover some basics of an array at this point. Again, this is something that we can just focus on separately. You know that we talked about the following. Of course, you know how to create integers, and we say this is stack of integers. So of course, we're going to be using integer data type all the time, and this is the reason why int. So int x equals 0 or something like that. We're used to this quite a bit. Then we said, well, you know what? You can create arrays dynamically. And for that, you can use a pointer. For example, int pointer. And how do I know it's a pointer? I use an asterisk in its declaration. So now ptr is a pointer to an integer. Now I can do this, new int. So there is a way to create new integer on the fly, which is kind of, I cannot even think at this point where I would use something like this, but you know, I can think about it. However, maybe more practical use would be to create an array of integers. And the syntax change is simply to say how many integers you want, right? And this number can be a variable, right? I can say size and define yet another integer named size and say I want 100, right? So the compiler will kind of go to a free store. That's the mechanism of C++ new operator to ask the environment for additional resources. In our case, 100 of more of new brand new integers, and this will give us access to a dynamic array of integers. We will be doing this in our second homework, but for now I would like to discuss this with you. So here's our program in memory, right? So somewhere there is code, somewhere there is area allocated to dynamic memory, so this we call it free store. And somewhere here, well, also, you know, there could be global data if we used any global data. So these are specific memory segments where specific data could reside. So this is our memory of a program that's running. And somewhere here, you know, is our stack. And stack is program stack. This is a temporary, I mean, the area where local scope of functions are established. And this is where your local variables live. Each time you call a function, whether it's being a member function or a freestanding function, a new stack frame or stack activation record is created for you, and upon return from a function, it is destroyed and returned back. So these are some areas that we can use. Your executable code also sits in memory. Now, free store, this can be focus of our attention at this point because we're saying new. New goes right here and tells the system, give me some resources from there, okay? Give me some memory, give me access to this memory through its initial address, and this will be stored in this pointer. So then the pointer can naturally be used as this. You know, give me access to the index 55 and store 1, 2, 3, 4, 5 in that location. Okay, so that's just how I can access all of my 100 integers, starting from 0 and ending with 99 apparently, because memory, this subscript access to memory is using 0-based index to begin with, and so it in our case of 100 integers, the actual numbers of integers will range from 0 to 99, one less than the size. If you use your fingers and count to 100 and start with 0, you'll realize the last one will be 99. Okay, so the only problem here is this: when we say new int, what's going to happen is that free store is the location which is managed by our runtime environment. When I say runtime environment, it's something that gets compiled into our program when we begin to use new. And so free store management takes place in terms of this. I can then say delete PTR. And if on a free store I allocated this brand new integer, right, first time, you know, my little int right here, it gets allocated. When I say delete memory at this location, I am returning it back to the free store, so I don't have a memory leak. Then I say new int, and this time I use this syntax. New understands this syntax, and it'll use this size to give me 100 integers. So the second time, this guy is returned back, right? Just you know, no longer belongs to me, but I can allocate 100 more. Int, and so forth. Int. I allocated 100 of them. But guess what happens in case if you say give me a block of memory, right? What happens is that this size 100 is also remembered by the free store. Then in order to return this memory back to the system, I must say delete, and there's this curious syntax with square brackets, delete this memory, and this means return memory back. Well, guess what? This allocation and the fact that we have to remember 100 integers and the ability of the free store deallocate resources for you, return memory back to the free store, and the next time someone says new, it can be recycled and so forth. In addition to that, sometimes free store can also get fragmented. There's all kind of issues with free store. It's not good. It's great for Java, because in Java it becomes a very uniform manner of allocating objects, and therefore Java can manage this very effectively. C++ says, well, you can do all this, but it's a little slow. Then listen, if we just wanted, and we know that we want 100 integers, there is a much better alternative to using new. And in our case, we can create an array directly on the stack. Essentially, create 100 integers inside local variable space of main. And don't bother about this fancy way of acquiring resources from free store and then even remembering to return claimed resources back to the free store. So an alternative would be to all of this. An alternative would be simply to say, I want 100 integers. I want to name them, and now we can, we can focus on our in stack. We can say, okay, storage, right? Some storage, and I simply want 100 integers. Okay? In this case, no free store is used. 100 integers are allocated immediately as soon as main is called. There is no cost of doing this in terms of managing the scope. So this is what Java doesn't have, right? It doesn't let you to create arrays or objects inside your local scope, like main or any other member function that you can use. So I could use this, right? And therefore, if this is the case, if this is what and this is what my intent is, I can simply Control C, copy it right here, and say, okay, I can have some storage, and I can have m_storage as my internal array to store 100 integers inside my in stack. It's terribly inefficient. It's terribly inefficient. Why? Well, because it has this significant limitation. Because with new, you can tell free store, I want 100 integers, or I want 1 integer, or I want 1,000 integers. Free store takes this as a parameter. So with new, the size of the block of memory is variable. You can provide new number every time. With arrays, there is the severe restriction, is that this has to be a constant number, cannot be a variable. Okay, so that's a severe restriction with arrays. So that's the difference between basically using pointer to a dynamically allocated block of memory and using this array. Okay, with this in mind, let's move on to, we still have some time left, right?
Can that be a constant value or no? It has to be just a number.
Over here.
Yes. Like if you define a constant, can you
Oh
use
yes,
that?
of course, of course.
Okay.
That would be. In fact, this is what I'm about to do
Okay.
in my code. Yeah, I just want to save. There's like a playback going on. Okay, so I'm going to